After watching this video, you'll know how to design and estimate filtering for surge lightning phenomena with proper generator and coupling decoupling network with surge coupling line to neutral or line to protective earth or neutral to protective earth. Subscribe and have a successful day with EMC. Before we start testing different components for surge pulse, let us see circuits for all main components that I created, surge generator and both coupling decoupling networks that we will use for testing. This circuit is inside our surge simulator. It is done according to the standard 61000-4-5. We have our energy storage capacitor, ideal switch, impulse duration shaping resistor 1 and impulse duration shaping resistor 2, impedance matching resistor, and rise time shaping inductor. We have our outputs plus and minus, and two parameters, discharge voltage and time delay. The values of components that you can see here are not given in the standard. You need to choose this component to have proper outputs graphs for surge pulse according to how the generator is validated. Let us test our circuit. You can see two circuits. This typical way to validate surge generator. We have timings that we need to fulfill and the shape of the graphs for voltage and current should be according to the standard. Let us see results. This is typical shape of a surge pulse current when we have a short circuit, and this is output voltage for open circuit at the output of the generator. Our discharge voltage is set to 2000 volts. And now let us check if our rise term and duration term are proper. Rise time for open circuit should be 1 microsecond plus minus 30%. Our maximum value is a little bit above 2 kilovolts, and the rise time should be measured between 10% and 19%. So 10%, 2 kilovolts is 200 volts. And 19% is 1.8 kilovolts. You can see that our rise time is around 900 nanoseconds, which is in the tolerance from the standard. Duration time for open circuits is valued between 50% of maximum voltage when the pulse is rising and then to the 50% when the pulse is falling. 50% should be 1 kilovolt. See, can I have here maybe closer? Very close, and we can see that our duration time is around 50 microseconds, which is according to the standard, and we have tolerance 20%. Our open circuit is correct. Let's see values for short circuit current. For rise time we should have 6.4 microsecond plus minus 20%. Maximum value is a little bit above 1 kiloampere. So 10% will be 100 amps and 90% should be 900 amperes. Our rise time is a little bit above 5.8 microseconds, which is correct because the minimum value is 5.1 microseconds. Next, let's check duration time for short circuit current. 50% of maximum amplitude will be 500 amperes. We are close with the amplitude. Our duration time is 16.5, which is close to 16, and we have 20% of tolerance, so this is correct. And one more parameter to fulfill is output impedance. Output impedance should be always 2 ohms, and we are very close with 2.02 ohms output impedance. This is done by measuring maximum voltage on the open circuit and maximum current on the short circuit. Our maximum value for voltage is 2040 and for current is 1007. Now let us check our coupling decoupling network, differential line to neutral or line to line for circuits with three-phase input, and coupling decoupling network, line to protective earth or neutral to protective earth. This is common mode network. The surge generator plus and minus will go here and here. Phase neutral protective earth inputs, where we put mains voltage here, and outputs that will go to our load. Also for common mode network, we have a parameter here. If we put 1, then the network will couple from phase to protective earth, and if we put 0, then the coupling will be from neutral to protective earth. Let's check first what circuit is inside the differential mode line to neutral network. We have our inputs, outputs, and plus minus for surge generator. Surge generator is coupled through 18 microfarads capacitor. This is the coupling part, and this is the coupling part consisting of 2 inductors 1.5 millihenry and 3 capacitors between phase neutral protective earth and phase protective earth 20 microfarads. This decoupling gives us that most of the energy of the surge pass will go to our device, not back to the mains. This is common mode coupling decoupling network. Our surge generator will put a path between phase and protective earth or neutral and protective earth. The coupling part is different. We have a lower capacitor, 9 microfarad, in series with 10 ohm, either for phase or neutral line. And I added switches that will respond to our parameter phase or neutral. If phase will be 1, this part will be low impedance and this will be high impedance, so pulse will not go this line. And if the parameter will be 0, then this will be high impedance line and this will be low impedance line, and our power will go to neutral and try to back through protective earth. Our decoupling part is the same. Also, I didn't mention the resistors for previous coupling decoupling network, and this one I added 1 micro ohm resistors because LTspice sometimes for these components is giving an error that these lines are floating if not connected. In this way, there is no error. Now we can start component testing. This is for differential lines, line to neutral. I prepared 4 circuits with load and capacitor, and varistor 10 ohms impedance, resistor capacitor better varistor 1 ohm, and additional series inductors. Before we see result, I want to mention that both generator and coupling decoupling network are real components. So if you test surge, The decoupling network will be on the table and surge generator will be close to it, like here in LTspice. Let's see results. This is voltage at the load, 2.7 kilovolts, very high, after coupling through capacitor inside our network. Capacitor have very high current. Our load less than 70 amperes, but is also high. If we add a varistor, what will happen with the voltage is lower, but is still pretty high. The load will see more than 2 kilovolts because this is a bad varistor with 10 ohms impedance. This is a simple model of varistor that you can use in LTspice. Breakdown voltage is here, 400 volts, and then impedance is one value, 10 ohms. Current through our load is a little bit lower than previous load, but still high. When we have a better varistor with lower impedance, let's see how the voltage looks like. It's lower than previous. You can see it better if I zoom it. Our voltage is much better now, around 1 kilovolt. Load is also 20 amperes, and we can count total energy that the load will see if we want. If we add series inductors, for example, as a part of EMI filter, voltage is similar than previous. It's less than 1 kilovolts, but a little bit above 900 volts. But the current should be low. It's lower also, but not to zero. It's also a little bit above 50 amperes. In this way, you can test different topologies for differential mode search and choose your best topology. You can add full field here, and we'll see this in our last circuit in this video. Also, I want to show you that you can see which components are taking in part of the ESD graphs. So for example, we check current on this varistor branch and the current on the capacitor part. We can see that capacitor is working very fast and is taking the part of the rising of surge pulse. Serious part, how much current is flowing? Not so much in comparison, but it's 18 amperes. Component testing common mode. I prepared 4 circuits. First with CY capacitor before our load, CY capacitors and bad varistors, CY capacitors and better varistors, and CY capacitors, varistors, and common mode choke with additional parallel high resistance, because without this LTspice will compute this infinity and will not have results. Our coupling decoupling network is different now. It's common mode decoupling network, phase to protective earth, because we put parameter as 1. Let's see results. First, our load with only CY capacitors. We can see that surge voltage is 1.1 kilovolts. Current is also high. Part of the current is going through one capacitor and part of the current will going to the second capacitor. We can see that's a little bit lower because C1 is connected to neutral line and the pulse is going from phase line. Let's delete currents for capacitors and let's see the second circuit voltage at the load first. You can see that is much lower because we added varistors, but this is not very good varistors. The impedance 10 ohms, but is better, 700 volts. Current at the resistor is also lower. Then we add better varistors with lower impedance. Voltage is now 500 volts and the current is higher than 10 amperes. And what will happen? We have our common mode in our filter. So first component with varistors, maybe a fuse there, CY capacitors, and a common mode choke. This will be a filter with additional varistor for transient protections. And let's see what is the voltage now. Voltage is even lower than before, and the current is also smaller. So the total energy is minimum when we have varistors, capacitors, and the common mode choke. And to show you that for our generator, we have also time delay, and with this time delay we can choose at which point of the sine wave our generator will put a pulse. We will 10 milliseconds, it's here. 15 milliseconds, it will be here, and 20 milliseconds, it will be on the end of the sine wave. You cannot see it. The highest amplitude will be at 5 milliseconds because we have amplitude of the sine wave in peak, additionally with our voltage pulse. This is how can look our input EMI filter with additional varistors for surge protection in differential mode and common mode. That is why we have three varistors between phases, in this case phase and neutral, between phase and protective earth, and neutral and protective earth. Next we have discharge resistor, CX capacitor, common mode choke, two CY capacitors, series inductors, some parasitics, our decoupling capacitors, and a load. Connection to protective earth, so to our housing, could be for our ground plate through screws to housing. If you think that you have additional parasitics here, maybe it's not direct, maybe you have some components here before the screw, then you need to think how parasitics or additional components in between have in your schematic and in the layout. Let's see results. This simulation takes about 40 seconds. These results for differential mode part, and this is common voltage, and also here the higher value is differential mode current and the lower value is common mode current through the resistor. The values both are low. Our voltage from surge was 2 kilovolts. Now for differential mode is 500 volts, and for common mode is less. 500 volt with sine wave above 300 at peak, it's pretty low. Total energy of this pulse is not so high anymore, and this is due to the currents. And you can check which component is taking which part of the ESD graph. Now let's check only currents for differential mode. You can see that our differential mode varistor is have 4 amperes. Common mode varistor is less, so most of the current is going through the differential mode varistor. That is proper when we have surge between line and neutral. Example, we can see how much current is flowing through the screws. For differential mode, nothing is really flowing here. We are 4.5 milliamperes first screw, and the second screw we are in microampere region. But for the common mode surge pulse, we can see that there is amperage here, 7.2 amperes, and here it's a little less because it's after first part of the filter, so it's 1.2 amperes, but still in amperes. We can say that our pulse is really going through screws, and this is how it looks. This is conclusion for my video. Remember that surge pulse needs always coupling decoupling network to couples into the line through capacitors. In the next video, I will focus on electrical fast transient, so-called burst. It's similar to surge, but with less energy. consider subscribing to my channel. See you next time. Bye.